Imagine standing in front of a block of granite the size of your house. Now imagine trying to cut it perfectly smooth with nothing but copper tools and wooden mallets. Sounds impossible, right? Yet somehow, over 4,600 years ago, the ancient Egyptians did exactly that thousands and thousands of times. They carved out blocks so precisely that today, engineers studying them still can't figure out how they pulled it off. But here's what just happened that's changing everything we thought we knew. When researchers fed this mystery into artificial intelligence, specifically Grok AI, the answer it generated didn't just explain the mystery, it revealed something that archaeologists had been overlooking for literally centuries. And when the evidence was examined, the scientific community couldn't believe what they were looking at. For more than 100 years, scholars have been locked in a heated debate about Egyptian stonework. The official narrative is simple enough. Ancient workers used copper saws, wooden wedges, and stones to manually cut granite. It's the kind of explanation that sounds reasonable until you actually try it yourself. Copper is one of the softest metals known to man. Granite is one of the hardest stones on Earth. The Mohs hardness scale rates granite at around 7, while copper sits at just 3. This means that granite is more than twice as hard as copper, making it theoretically impossible for copper to cut through it efficiently. Yet the evidence in places like the Aswan granite quarries tells a completely different story. There are finished obelisks, perfectly cut blocks, and unfinished pieces that show tool marks so precise they seem to defy the limitations of the tools historians say were used. This contradiction has been the elephant in the room of Egyptology for generations. Some researchers quietly questioned whether ancient Egyptians might have possessed technology we haven't discovered yet. Others doubled down on the copper tool. Explanation? Insisting that with enough sand, water, and human labor, anything was possible. The mainstream academic consensus held firm to the copper narrative, but underneath, doubt was growing. Students of archaeology heard the official explanation, nodded along, but couldn't shake the feeling that something wasn't quite adding up. Then came the moment everything changed. A team of researchers decided to approach the problem differently. Instead of relying on existing archaeological theories or guesswork, they asked an advanced artificial intelligence system to analyze what we actually know about Egyptian stoneworking and propose how it might have been accomplished. When Grok AI processed this information, it generated a response that incorporated multiple techniques working in conjunction. But more importantly, it highlighted something that archaeological literature had touched on but never fully emphasized, the role of understanding stone weakness and strategic geology in the cutting process. But that's not what shocked everyone. What shocked everyone was when researchers decided to test the AI's recommendations against evidence that had been sitting in museums for over a century, evidence that had been classified and filed away without proper investigation. Here's where it gets fascinating. In the unfinished obelisk at Aswan, there are visible marks and tool impressions that had always been documented but never fully analyzed in the way that Grok AI suggested. The AI pointed out that the grooves and holes weren't simply random marks, but represented a very specific strategic approach to stoneworking that involved understanding fracture mechanics, identifying planes of weakness within the granite, and using multiple cutting methods in sequence. When archaeologists re-examined the sites with this framework in mind, they discovered evidence of a level of planning and geological knowledge that was far more sophisticated than previously credited to these ancient workers. The method that was actually used appears to have been a multi-stage process. First, workers would identify the grain direction and natural fault lines in the granite. This wasn't guesswork. Egyptian quarries show systematic evidence of what appears to be deliberate surveying and planning. The workers would mark out the exact path where they wanted to cut using measurements and tools that left marks we can still see today. Then came the cutting phase. Contrary to what conventional archaeology taught, the cutting wasn't done primarily with copper saws. The copper tools played a supporting role. The primary cutting method combined 3 techniques that worked together in a coordinated system. The first technique involved using harder stone hammers, specifically dolerite, to pound out an initial groove or channel along the marked line. Dolerite is a dark, fine-grained igneous rock that is significantly harder than granite, roughly 7.5 on the Mohs scale. Egyptian workers would have found dolerite stone locally or known where to source it. They would shape these stones into hammers, and with thousands upon thousands of carefully controlled blows, they would gradually pound away at the granite surface, creating a groove. This process was incredibly labor-intensive and required tremendous skill. Well, you couldn't just hammer randomly and expect results. The angle of the blow, the force applied, the spacing of the strikes, and the angle of the tool all mattered. But this is where Egyptian planning and training came in. Archaeological evidence suggests that stoneworkers were highly organized professionals, not slaves mindlessly striking rocks. They would have trained for years to develop the muscle memory and skill required to perform this work efficiently. Once the initial groove was created, the second technique came into play. This is where the copper tools became crucial, but not in the way historians traditionally thought. Copper tools, combined with an abrasive slurry made from sand and crushed quartz, could actually cut through granite. The sand contains quartz, which is just slightly harder than granite. When mixed with water and applied with a copper saw or scraping tool, the resulting combination creates an abrasive paste that can gradually wear through even the hardest stone. This isn't rapid or easy, but it works. Experimental archaeology has proven this repeatedly, though for some reason, the significance of these experiments didn't fully penetrate mainstream understanding. The copper tools, working with this abrasive medium, would refine the groove created by the dolerite hammers, making it more precise and deepening the cut. But there was a third and final crucial technique that pulled everything together, and this is what Grok AI highlighted that had been overlooked. Once the groove was sufficiently deep, workers would drill holes along the intended break line. These holes would be made using copper tube drills, again using the sand and quartz abrasive technique. The evidence for this is literally everywhere in the quarries, if you know where to look. Then, and here's the crucial part, they would insert wooden wedges into these holes. These weren't just any wooden wedges. The Egyptians would select specific types of wood that had particular properties. The wedges would be driven in carefully, and then they would be saturated with water. When wood absorbs water, it expands. This expansion, multiplied across dozens of wedges along a cut line, exerted enormous pressure on the stone. The pressure would follow the path of least resistance, which in a properly prepared cut is right along the groove. The stone would split with surprising cleanness and precision, following the exact line where the workers had planned. This is the process that Grok AI identified, and that fresh analysis of historical evidence confirmed. It wasn't rocket science, but it required knowledge, planning, organization, and incredible skill. It required understanding materials, understanding mechanics, and understanding how to work with nature rather than purely against it. It required a workforce that was trained and motivated, operating under sophisticated management structures. It required mathematical and geometric knowledge to ensure precise measurements. All of these elements existed in ancient Egyptian civilization. We have evidence of their written records, their organizational structures, their training, methods, and their material knowledge. What had been missing was a comprehensive framework that brought all of these elements together and explained how it all worked as a cohesive system. What makes this revelation so significant is what it says about ancient engineering knowledge. For decades, the minimalist interpretation dominated academic discourse. This interpretation suggested that ancient engineers were essentially doing the best they could with very limited understanding and primitive tools. The implication was that their achievements, while impressive given their constraints, were the result of brute force and massive labor investment rather than sophisticated understanding. Grok AI's analysis, confirmed by fresh examination of the evidence, suggests something quite different. The ancient Egyptians didn't achieve their results despite their tools and knowledge limitations. They achieved their results because they had developed a comprehensive system of stoneworking that was perfectly calibrated to the materials they were working with and the tools available to them. This system required significant knowledge about geology, mechanics, material properties, and engineering principles. It required the kind of planning and organization that only sophisticated civilizations can maintain. Think about what this means. The Great Pyramid of Khufu contains approximately 2.3 million blocks of stone. The precision and fit of these blocks is so remarkable that you can't fit a sheet of paper between many of them, even after 4,600 years of weathering and settling. If the mainstream minimalist interpretation was correct, these blocks would have been cut with crude, simple methods that would produce highly variable results. Yet they didn't. The consistency across millions of blocks suggests not crude methods, but refined, well-understood techniques applied by workers who knew exactly what they were doing. The fact that we have unfinished pieces in quarries and construction sites actually gives us windows into the process. We can see the stages of work, the progression from rough quarrying to final finishing. And when you look at these pieces with the framework that Grok AI provided, the process becomes comprehensible. It makes sense. It works. This has profound implications for how we understand human ingenuity and knowledge transfer in ancient civilizations. We tend to view knowledge progression as essentially linear, with each generation learning from the previous one in an accumulating way. But what evidence from Egypt and other ancient civilizations shows us is that knowledge can develop rapidly under the right conditions, reach sophisticated levels, and then be lost or degraded if the cultural conditions that sustained it change. Egyptian stoneworking represents a culmination of knowledge that had been building for centuries before the Pyramid Age. By the time Khufu came to power, the techniques were refined, the workers were well trained, and the system was efficient. This didn't happen by accident. It happened because multiple generations of engineers and workers had been developing and refining these methods. The timeline is instructive. The Egyptian pyramids weren't built overnight or even suddenly. The pyramids evolved. Early pyramids were step pyramids, relatively modest in scope. The bent pyramid at Dashur shows evidence of refinement during construction, suggesting evolving understanding. By the time the Great Pyramid was built, the engineers had several centuries of pyramid building experience. The techniques had been tested and refined repeatedly. The labor systems were well established. The quarrying and stoneworking had become sophisticated industries. This is not the narrative of simple primitive people doing the best they could. This is the narrative of a civilization that had developed real expertise. What Grok AI did was take all the disparate pieces of evidence, the experimental archaeology, the tool marks in stone, the unfinished pieces, the written records about labor organization, the geological analysis of the quarries, and it assembled them into a coherent narrative that actually explained the results we see. And remarkably, this coherent narrative doesn't require advanced technology, doesn't require mysterious lost knowledge, doesn't require any explanations outside the realm of what we know ancient Egyptians possessed. It simply requires taking seriously what the evidence has been showing us all along and putting together the pieces into a system that makes logical sense. One of the most important aspects of this discovery is what it reveals about human problem solving and adaptation. The Egyptians didn't have diamond-tipped saws or modern quarrying equipment. They couldn't have cut granite the way modern crews do, so they developed an alternative approach that worked within their constraints. They substituted mechanical hardness with strategic methodology. They substituted rapid cutting with patient, planned procedures. They substituted individual power with organized labor and mathematical precision. This is genuine engineering. This is genuine innovation. It's just that it's working within a completely different technological paradigm than what we're used to. The confirmation of Grok AI's analysis also highlights something important about artificial intelligence and historical analysis. AI systems can process vast amounts of information and identify patterns that human researchers might miss, especially when those humans are constrained by academic traditions and established frameworks. The AI wasn't bound by decades of academic debate. It wasn't invested in defending any particular theory. It simply looked at the evidence and proposed what seemed most logical based on material properties, mechanical principles, and archaeological findings. And its answer turned out to be remarkably accurate when tested against actual evidence. But perhaps what's most fascinating is what this says about the questions we ask and the frameworks we use to interpret evidence. For over a century, scholars were asking the wrong question. They were asking, how could copper possibly cut granite? And when that question led nowhere, rather than reconsidering the framework, they just accepted a narrative they didn't quite believe. The better question, the one Grok AI essentially asked, was, what combination of techniques would actually work? And that question led immediately to the answer that had been sitting in the archaeological record all along. The evidence has been available. In 1883, Flinders Petrie examined granite cores and noticed something remarkable. The cores showed evidence of being drilled by tubular tools with extraordinary precision. The marks on the cores showed evidence of the technique being used. Petrie documented this. It was published. But for over a century, this evidence was treated as a historical curiosity rather than a key piece of the puzzle. Nobody fully connected it to the other elements of the stoneworking system until Grok AI suggested the framework that brought everything together. We see similar grooves and drill holes in the Aswan quarries. The unfinished obelisk shows an elephant stone, a piece of granite that was left behind after workers struck a fault line or determined it was flawed. The tool marks are visible, the holes are visible, the grooves are visible. When you know what you're looking at, the picture becomes clear. This isn't mysterious. This isn't indicating advanced lost technology. This is indicating skilled workers using a well-developed system of stoneworking. What makes this particularly important now is that we live in an age where we're increasingly reliant on artificial intelligence to help us understand complex problems. Grok AI's analysis demonstrates both the power and the importance of careful, skeptical evaluation of AI outputs. The AI didn't provide a proof. It didn't provide a definitive answer. It provided a framework and a suggestion. That suggestion, then, had to be tested against evidence, examined critically, and validated through research. The AI's output was a starting point, not a conclusion. This is how AI should be used in fields like history and archaeology, as a tool for organizing information and suggesting frameworks, not as a source of authority. The practical implications of this understanding are significant. In modern conservation and restoration of Egyptian sites, understanding how the original construction was done helps inform how to preserve it. It helps us understand stresses and weaknesses. It helps us restore damaged pieces using techniques consistent with the original construction. It also helps us teach people about ancient engineering. Rather than presenting Egyptian stone working as a mysterious feat that we don't really understand, we can now present it as a sophisticated system that was brilliantly adapted to available materials and tools. It also changes how we think about the classification of civilizations. We often rank civilizations based on their technology, with the assumption that simpler technology means simpler society. But Egypt demonstrates that technological sophistication isn't only about what tools you have, it's about how intelligently and systematically you use the tools available to you. A Roman engineer with modern quarrying equipment might get the job done faster, but the Egyptian engineer with copper saws and dolerite hammers achieved results that are competitive with what modern crews can do in terms of precision and quality. The method was different, but the engineering understanding was genuine. There's also a lesson here about the relationship between evidence and interpretation. For 100 years, the evidence was there. Photographs of the unfinished obelisk were in books. The tool marks were visible. The holes were documented. The grooves were recorded. But without the right interpretive framework. So the evidence didn't form a coherent picture. It just seemed like a confusing collection of marks and holes. Grok AI's contribution was essentially providing that interpretive framework. It took the disparate pieces and suggested a way they could fit together. It was the conceptual breakthrough that was needed. Scientists and historians are now realizing that questions about ancient technology are questions that can benefit from the kind of analysis that AI can provide. Artificial intelligence is extremely good at pattern recognition and at synthesizing information from multiple sources. It can propose frameworks that integrate material science, mechanical principles, archaeological evidence, and historical records in ways that require significant computational and analytical capability. This doesn't mean AI has the answers, but it means AI can help humans ask better questions and explore more possibilities than might occur to them working alone. The discovery also highlights the importance of maintaining an open mind in historical research. For decades, anyone who questioned the official explanation was often dismissed as lacking credentials or academic rigor. But sometimes the official explanation just misses the forest for the trees. Sometimes you need to step back and look at the big picture. Sometimes you need to bring in new perspectives and new tools. Grok AI provided that new perspective, and the result was that we now understand ancient Egyptian stone working more comprehensively than we did before. What's particularly interesting is that none of this requires abandoning mainstream archaeology or accepting alternative history theories. The techniques we're discussing are entirely consistent with what archaeologists have understood about Egyptian capabilities. The tools used are documented. The materials are known. The labor systems are understood. The only thing that's changed is how we put these elements together into a coherent system. This is how good science works. New evidence or new analysis refines understanding without necessarily overturning the entire field. Looking forward, this discovery opens up new research directions. Archaeologists and materials scientists can now conduct more targeted experimental archaeology, testing the efficiency and effectiveness of the multi-stage process that Grok AI identified. They can examine quarries and construction sites with a focus on evidence that supports or challenges this framework. They can analyze the chemical composition of tool marks to determine exactly which materials were used at each stage. They can study the training marks and tool implements that have been found to understand the labor system more completely. This case study also demonstrates the value of interdisciplinary approaches to historical problems. Grok AI works because it can integrate knowledge from multiple fields. It can apply principles from material science, mechanical engineering, geology, and archaeology simultaneously. Human. Researchers, by necessity, tend to specialize, but the most interesting problems often sit at the intersection of multiple disciplines. Bringing in AI that can synthesize across disciplinary boundaries can yield insights that specialists might miss. The broader implication is that we should probably reconsider a lot of ancient technologies with fresh eyes. If we were so wrong about Egyptian stoneworking, what else might we be misunderstanding? What other evidence are we sitting on that we haven't properly interpreted? What other mysteries might yield to the kind of comprehensive, multidisciplinary analysis that Grok AI provided? This discovery should spark a methodological rethinking across archaeology and historical studies. It should encourage researchers to question accepted narratives, to test assumptions, to look at familiar evidence with new frameworks. And perhaps, most importantly, it should remind us of something fundamental about human beings. We are problem solvers. We are innovative. We are capable of developing sophisticated solutions to difficult problems, even with limited resources. The ancient Egyptians didn't accomplish what they did because they had magic or supernatural technology. They accomplished it because they were brilliant engineers and skilled workers who understood materials and mechanics and who developed systems that worked within their constraints. We should honor that accomplishment not by pretending it's mysterious, but by understanding it properly. And that's exactly what Grok AI helped us do. The story of how Egyptians cut granite is ultimately a story about human ingenuity, systematic thinking, and the power of asking the right questions. When we ask the right questions and apply rigorous analysis, we can understand almost anything. When we lock ourselves into particular frameworks and assume we already have all the answers, we miss opportunities for genuine understanding. Grok AI didn't provide magic. It provided a framework. And that framework, combined with careful research and rigorous testing, brought us closer to the truth about one of history's greatest engineering accomplishments. And that, it turns out, is even more remarkable than mystery.